Another important symmetry operation is the so-called mirror plane. If we look at an equilateral triangle here, we notice that if we draw a line that bisects any one of the angles, and it also bisects the side here, that this line, if we put a mirror there, that this side on the right would be reflected. If we looked in a mirror, we could see an image that would look just like the left side that is actually present. So this is a symmetry operation which is called a mirror plane. So if the plane of the board is the XY plane, so we assume that this is the X direction and that this is the Y direction, then in this particular case we have a mirror plane, which I'll also denote with a ruler here, that is in the YZ plane. So we call this a YZ mirror. And the symbol that we use for a mirror is the Greek letter sigma, and then we often make subscripts to denote which particular mirror plane we're talking about. In this case, we're talking about the YZ plane, so we call it sigma YZ. The reason for using this particular symbol is that sigma is the Greek letter S, and the word that we often use for a mirror or a mirror plane in group theory is Spiegel. And Spiegel is the German word for mirror. Spiegel begins with the letter S. So there's a beginning letter in common between sigma and Spiegel, which means mirror. Now, if we have an equilateral triangle such that all three angles are identical and all three sides are equal, then we actually have three different of these types of mirror planes. So we can also draw a mirror plane that goes roughly this way. So we reflect this part of the triangle into this part. So that's a second mirror plane. And then we'd have a mirror plane that would go along this line and bisect the other side. So one way that we can recognize an equilateral triangle, as opposed to any other type of triangle, is that it has three of these mirror planes. Now this will not necessarily be true for any triangle that we might envision. So let's look at another type of triangle. So in this case, you want to be specific and use an isosceles triangle. So an isosceles triangle, something like this. So we have an isosceles triangle. And the important thing about an isosceles triangle is that we have two sides which are identical. And we often represent that by putting a little tick mark to show the two lines that are identical. And then this second side is a different length, so we put two ticks. So this side and that side are equal, but the third side is not. So we have an isosceles triangle that is not an equilateral triangle. In this particular case, again, we're going to have a mirror plane. And if I draw the mirror plane, it will go through this particular line. And again, this is going to be a sigma YZ. If we orient our axes such that X is in this direction and Y is in this direction. So we have a sigma YZ mirror plane. But notice something, that if we try to look for a mirror plane that goes along this particular line, it is not a true mirror, because if I reflect this side into the mirror, I'm going to get a length this long, and it will not match up where the vertex is. So I will not have a mirror plane along this plane, and I will not have a mirror plane, for example, along this line either. So I've reduced my three mirror planes down to one in the case of an isosceles triangle. So we can distinguish an isosceles triangle from an equilateral triangle by the number of these mirror planes. So let's look at the last type of triangle. So with a triangle, we can have all three sides the same, we can have two sides the same, or we can have all three sides different, so that none of the sides are the same. So let me draw an example of this kind of a triangle, some generic triangle, and where all three different sides have different lengths. So it's 1, 2, and 3. And in this case, this is called a scalene triangle. For a scalene triangle, no matter how we try to arrange our mirror planes along For example, along here, or along here, we don't have a true mirror. Now there's a nice mechanical way of representing mirror planes, which we can use just with a piece of construction paper. And we'll see more details of this type further on in the video series. But for example, if we take a triangle that's shape of construction paper, and we notice that if we fold it along the line here, fold a line, that it lines up perfectly along the fold. So if I open back up, this particular line will be along the mirror plane. So the actual mirror plane will be a plane that goes along this line, that passes through this line, perpendicular to the plane of the triangle, and it will reflect this side into that side into this side. And we could do that for, this is an isosceles triangle, but if I did it for an equilateral triangle, I would be able to make 3 such folds, and there'd be a mirror plane bisecting each of the 3 angles. So that gives us the situation for a scalene or isosceles and or equilateral triangles. But what happens if we have a square? So a square is another important geometric shape. So let's look at our square. So here I have a square, and for the sake of completeness, let's draw the x-axis, and then we have the y-axis in this particular direction. So we're looking for one or more mirror planes for a square. Well, the first thing that we would notice is that we can draw a mirror plane along the y-axis. So this would be the YZ plane. So I draw a YZ plane here, and I notice that it reflects the left-hand side of the square into the right-hand side of the square. So along this line, I would have a YZ mirror plane. On the other hand, we would notice that I could do the same thing going along here. So if I draw a line along here and raise a plane perpendicular to this line, it would actually reflect the bottom part of the square into the top of the square. And this would give me a sigma xz. Okay, so I see, so far I have, for a square, at least 2 mirror planes. Do I have any more? Well, since it's a square, I can also draw a line along the diagonal, and I can actually raise a mirror plane perpendicular to the plane of the board, which is the xz plane, and I have yet another plane. We're not going to label that specifically, but let's just call that sigma for the time being. So I have a mirror plane along there, and by the same token, I can go along this diagonal and also find a mirror plane. So we see that for a square, we have 4 distinct mirror planes that will reflect one part of the square into another part of the square. So one you might ask is, I found 4 mirror planes. Is that all the mirror planes that are available for a square? And it turns out there is one more, which is a little difficult to show, but we will mention it because it's extremely important. We can imagine the square to have an infinitely thin thickness, but if we imagine to have a very, very small but non-zero thickness, I can essentially cut through the square so much that, like I'm doing a fillet. If you've ever filleted a fish, make a very, very super thin fillet cutting along this way. The top part of the square will look exactly like the bottom part of the square. Each one will be infinitely thin, but they will be identical. So we'd have a mirror plane that actually passes along the plane of the whiteboard. It's actually the same plane in which the plane figure resides. So we have one additional mirror plane, which we can call sigma xy. Sigma xy. Now it turns out there's something very special about this plane, in addition to the fact that it is often overlooked because it's not as obvious as some of the other mirror planes. Recall that one of the ways that we can define a square is that it has a C4 rotation. So we know that passing through the center point here, if I use this dial to represent the axis of rotation, I can rotate, for example, counterclockwise 90 degrees, and that gives me a C4 rotation. If I rotate by 180 degrees, it gives me a C2 rotation. One thing which we had not yet mentioned about proper rotations is that a C4 rotation, having a 4 as the subscript, is more important than a C2 rotation. So the larger the n value is for the proper rotation in the Cn designation, the more important that particular rotation is. So the rotation that has the highest n value for a particular figure, we call the high order rotation axis. So for a square, we notice that C4 is the high order rotation axis. And it turns out that when we have the high order rotation axis, once we've defined what that is for our particular figure, then we use that as our basic point of reference for all the other symmetry elements in the shape. So in this case, one thing that we notice is that relative to the high order rotation axis, this sigma xy mirror plane is perpendicular to it. We can also say more mathematically that it's normal. So normal, perpendicular mean exactly the same thing. Whenever we have a mirror plane that is perpendicular, normal, to the highest order rotation axis, this particular mirror plane gets a special name. In addition to naming it as sigma xy, which is definitive as far as our axes go, we also call this sigma h. And the h in sigma h stands for horizontal. Now, very, very important thing. The horizontal doesn't mean it's horizontal relative to some sort of orientation that we make of the object. It means specifically that it's perpendicular to the high order rotation axis. And it will turn out that no matter what type of mirror plane we have, there are only two possibilities. Relative to the high order rotation axis, it can be perpendicular to it, in which case we have a horizontal mirror, or it can include the high order rotation axis. So for example, we notice if I have this particular mirror plane here going along, relative to the high order rotation axis, I notice that the axis is actually in the exact same plane. In those cases, we know that we definitely do not have a horizontal mirror. When we have a horizontal mirror, the horizontal mirror and the high order rotation axis only have one point in common. And the axis itself basically is not in the plane. When it is in the plane, we have two related names that we use for that type of mirror plane, which become clear later on. The most common name we use is vertical mirror. The second name is a special type of vertical mirror which we call a dihedral mirror. So for symbols, for later purposes, let's just kind of know what these would look like. So if it's a vertical mirror, we use sigma v, which is a common designation. And slightly less commonly, but in special cases, we have what we call a dihedral mirror, so we use this symbol sigma d. And we'll show later on why we use one term as opposed to the other. But the most important thing is that for any particular shape, the first thing that we want to ascertain is the high order rotation axis. Right after that, we want to ascertain which, if any, mirrors is perpendicular to the high order rotation axis, in which case we have a horizontal mirror. Okay, so let's look at the next most sophisticated shape that's very common after the square, which is the hexagon. So I'll see if I can draw a hexagon relatively clearly here. One thing you'll notice is that I am not a great artist, and I often tell students that if I was a great artist, I would be an artist and not a chemist. So, but try as best you can to draw as best you can. It's developing a sketch for most problems makes the problem much easier to solve. So in the case of the hexagon, using my own idea that I just mentioned, is we want to look for the high order rotation axis. And from our previous video, we know that the high order rotation axis for a hexagon is C6. And we notice that our C6 goes along this particular axis. And typically we arrange the high order rotation axis to be the z-axis. There are some exceptions to that, but in general, as often as possible, we try to arrange our axes such that the high order rotation axis is along the z-axis. In that case, that puts the plane figure, if we're talking about a plane figure, in the xy plane. So again, let's define our axes. We can put the x-axis along here, the y-axis along there. And now we want to look for mirror planes. So we could recognize right away that we have mirror planes, for example, along the y-axis. So we would have a sigma yz along here. So we have a mirror plane along there. And we notice, since it includes the high order rotation axis, this is not going to be a dihedral mirror. I mean, it's not going to be a horizontal mirror, so it has to be either a vertical or a dihedral mirror. We can also have a mirror plane that goes along this line and then perpendicular to that, so coming up into the z-axis also. So this is going to be sigma xz. Okay. And since, again, it's not perpendicular to the high order rotation axis, it's not going to be a horizontal mirror. So we've seen two different mirrors. We also have a number of different mirrors. So we have a mirrors that go through the center of each face. So we have two more mirrors that go along here. Okay. We also have mirrors that go through the vertices. So I have a mirror that goes along here, a mirror that goes along here. Now, in this particular case, the mirrors that go through the vertices, so they go through the vertex on each side, we call sigma v. Those are called vertical mirrors. Okay, they're called vertical mirrors. When we have a mirror plane that goes through the midpoints of the sides, so it doesn't actually go through the vertices, but goes in between them, that's called a dihedral mirror. So here we see the difference between a dihedral mirror and a vertical mirror. This distinction between symmetry operations that go through atoms, go through vertices, and those that don't will become clearer later on. But using this idea, we can label the other mirrors accordingly. So we see that this particular sigma xz goes through two vertices, so it must be a sigma v. That's a sigma v. Sigma v. And then, sorry, sigma v there. The sigma yz goes between the vertices, so it must be a sigma d. It must be a dihedral mirror. Similarly, this particular mirror goes through two vertices, so that must be a sigma v, or vertical mirror. And this particular mirror goes between the vertices, so that must be a sigma d. So we're able to label the vertical mirrors and the dihedral mirrors for the hexagon. But we have one mirror left, and that's going to be the most important mirror of all, which is our sigma h. And in using the coordinate system that we developed, it's going to be the mirror plane essentially which cuts through the infinitely thin hexagon along the xy plane. So sigma xy is going to be our horizontal mirror, and we notice it's nice when we draw it on a whiteboard or a piece of paper that very often, not always, but very often, the horizontal mirror will be the plane of the paper or the plane of the board, and we notice that it really is perpendicular, it really is normal to the high order rotation axis, which would go along this particular dowel. It really is normal to the high order rotation axis, which would go along this particular dowel.